The title of this presentation is Learning Phase Transitions with the Bohr Machine. To begin with a presentation overview, we'll be introducing the Bohr machine and the corresponding training procedures for such machines, which can be used for more closely studying different sectors of the phase space for quantum and classical models. And this relates to studying interactions and dynamics of quantum many-body systems, which we'll be alluding to and describing more throughout this presentation. And to do this and to orient ourselves with this field and the ability to make use of different types of models for generating training set data that we can pass to a model for identifying different properties and phases of matter, we'll be discussing a 2021 reference which studies different behaviors of the XY model using the Bohr machine. And we'll be able to draw the viewer's attention to the potential of this method for being able to study critical, subcritical, or supercritical behaviors of other models, including the quantum 6-vertex model, loop models, the dilute Potts model, and even other models, which we'll allude to at the end of the presentation, including the quantum Ashton-Teller model and related models. So this is the paper reference in which is titled Bohr Machines for Periodic and Open XY Quantum Spin Chains by these three authors. And these authors are interested in making use of the fact that we can look to different models of either quantum mechanics or models that are related to quantum physics and statistical physics for generating training set data that we can evaluate and further pass along to a Bohr machine to look for the ability or the ability of this Bohr machine to be able to detect different regions of the phase diagram from training the model on different parameters. So we'll introduce the model, which is the XY model, and describe some of its characteristics and relate it to some characteristics of the quantum spin chain. And then we'll be able to introduce other related models from which we can look at how to define the probability, the training loss, and the matrix product state, or the MPS, which is used to encode different types of properties and characteristics of the quantum spin chain. So we're going to introduce the model and the spin chain just to begin, so we can look at different types of ways to arrange and enforce boundary conditions on a spin chain. For one, we can look at, as given by the authors in their 2021 reference, the type of spin chain that's given in figure A or in figure B. And these spin chains differ in that one of them in figure B has periodic boundary conditions in which the first node and the last node of the spin chain are all connected together, hence establishing connectivity between all the nodes of the spin chain. Whereas the spin chain that's given on the left-hand side only has connectivity between the nearest neighbors for most of the sites on the spin chain, except that there's no periodicity in the boundary conditions, which is enforced in the last node and the final node of the spin chain. So this is demonstrating the type of model that we would like to simulate, in which we're going to be making use of a Hamiltonian that we define for the XY model and determining how we can look at different types of parameters and how the Hamiltonian would behave under different parameters and how this would relate to different phases and different behaviors of the phase space that the XY model can undergo and exhibit. And so the Hamiltonian for the XY model is given by this Hamiltonian. So we're fixing some parameter gamma, which is taken to be strictly positive, as well as the fact that from each one of these gamma parameters, there are two products of spins. One of them is a spin in the x dimension, or in the x coordinate, and the other is a spin in the y dimension. And then these constitute the different types of spins that we can have in the XY model. And we're looking at nearest neighbor interactions because all of the spins are taken between I and I plus 1, and the Hamiltonian is given by the fact that there's a summation from I is equal to n, I is equal to 1 to n minus 1 of minus j, which represents one of the coupling constants for the Hamiltonian, as well as an external field, which is given by the spins in a z component, which is also taking a summation over i's 1 to n, but the difference is that there's no coupling constant of minus j. Instead, there's a coupling constant of the external field of minus h over 2. And from this Hamiltonian, as well as from characteristics of the quantum spin chain that we have introduced, which we'll use to encode different properties of these states of matter and the quantum spin chains in general into the matrix product state, we can look to the phase diagram, which is given by the following plot. This is another figure from the reference of the authors, in which they provide a plot for us of gamma by h. So gamma and h are two parameters which are appearing in the Hamiltonian, one of them is appearing as a perfactor for the sigma x terms, and the other is appearing as, one of them is appearing as a perfactor for the sigma x term, and the other is appearing as a perfactor for the sigma y term, and the h term is appearing as a perfactor for the external field for the sigma z terms. And we can see that as in many different types of phase diagrams for models of quantum physics or statistical physics, there can be different types of ways in which the phase space can be partitioned into different types of behaviors. In one can see that at the line h is equal to 1, this is given by the critical line for the XY model. And then above this line, there can either be different types of partitions of the phase space, namely a disordered phase, a critical easing phase, or below the critical XY line, which is given by below the h is equal to 1 line, we have a critical XX model phase, or we have ordered phases or oscillatory phases. The oscillatory phase is given by the area that's spanned by the unit circle in the first quadrant. So this is just demonstrating how, if we want to make use of a Bohr machine and being able to train this model for identifying different types of phases of matter, exactly what the authors of the 2021 reference are interested in doing is that they look to train the model under different parameters from this Hamiltonian from different regions of phases of space, and then they're able to pass this training set data to the model for then assessing performance of the model and being able to capture or qualitatively describe or characterize different regions of the phase space and the different types of properties of the matter in the quantum spin chains that would be captured by the Hamiltonian. But besides the XY phase diagram, training set data for the machine can be generated by repeatedly evaluating the Hamiltonian under different states. And this is just what we have been mentioning, in which we can see from the disordered, oscillatory, or ordered phases and how of the XY model, and how it can either have shared connections with the Ising model or the XX model, how there can be different ways to repeatedly evaluate this Hamiltonian, which would relate to simulating the energy of different configurations from the quantum many-body system, and how this would be relating to studying the excitations of different sites of the spin chain that we had given. So we're just going to be able to introduce, what we just want to do is to be able to introduce the framework that the authors use for training this Bohr machine, and then highlight the prospects of directly being able to apply this framework for other types of models in statistical physics and quantum physics, which share different types of behaviors in their phase diagrams, and how this can demonstrate being able to make use of AI and machine learning type models at the intersection of physics for identifying different properties and behaviors of matter. And the overall workflow that they're using that we've been describing is that they make use of some density matrix renormalization group, which is given by the acronym DMRG, and then they evaluate the Hamiltonian to form a matrix Sprotte state, and then they know the ground state of the system because the ground state of the XY model can be quantified by the behaviors in terms of the Hamiltonian that we introduced, and then they can learn a matrix product state, which hence allows them to learn some type of probability measure for the ground state. So this can immediately share in similarities and share in commonalities, and resemble the different types of characteristic and properties of ground states that we would expect to be able to simulate from other types of models, which we're going to introduce at the end, to which this framework can be directly applied. And the computational objects for the workflow, as we have been describing, is a probability measure, which is given by a summation over quantum states. And then they normalize this numerator of the expression by the partition function so that they can obtain a probability measure for the learned probability measure p hat for the ground state. And then they can also look to evaluate some training loss, which is given by -1 over the cardinality of the points in the training set that they use, and as well as a summation over the log of the learned probability p hat of v. And then the matrix product state is given by the summation over however many sites of the chain of the quantum spin chain that are given. And then this type of matrix product state can also easily be encoded for other types of models, which we're going to introduce in the next slide or two, which allows us to directly make use of and apply this framework for learning a probability measure for the ground state of different types of systems, whether it be systems in statistical physics or quantum many-body dynamics or quantum physics, and how this can relate to training a different type of model and evaluating the training loss of the Bohr machine at each iteration of training for learning about how well the model can perform in characterizing different phase behaviors. And as we have been mentioning, the whole punchline for this is that there are many prospects for being able to apply this methodology to the framework of other models and diagrams, aside from the XY model that the authors introduced in their paper, in which we can look at the 6-vertex model, from which we can obtain a probability measure and look at types of ground states for the 6-vertex model, or i.e. configurations of the 6-vertex model that would minimize the free energy of the model, which can be given by a probability measure of the weight of the 6-vertex configuration normalized by the partition function. But we can also pass the quantum version of the 6-vertex model, which is defined a little bit differently, because instead of defining and parameterizing the probability measure for the 6-vertex model, the classical 6-vertex model, in terms of a weight, we can also look to take a Hamiltonian, which is given by a summation over plaquettes. And in each one of these plaquettes, we're looking at different bracket states, which can represent the different orientations of arrows which we can obtain in the quantum 6-vertex model. And we can introduce a probability measure and its expectation from the fact that we can take some state C, which lives in Hilbert space, and we can take a bracket state up C with the Hamiltonian of the quantum 6-vertex model. And finally, we can also look to introduce the dilute Potts model, which is given by the high temperature expansion of the Lupo-N model, which is given by a nearest neighbor product of these terms, where they represent Ti, Tj represent the occupancy terms, which are either set to 0 or 1, depending upon whether a nearest neighbor site is occupied over the hexagonal lattice for I and j being nearest neighbors, as well as an exponential factor, which is demonstrating the number of monochromatically colored triangles and the number of the summation of spins of a configuration. So this is just to say that if we look at different types of parameters for any one of these probability measures for the 6-vertex model, the quantum 6-vertex model, or the dilute Potts model, we're able to make use of this Born machine framework for looking at what would we expect the ground state to be for different types of configurations of these models for quantum many-body dynamics and statistical physics, and then being able to train the model and look at its performance and being able to characterize and learn different regions of the phase diagram for these models on its own without having to explicitly feed this type of model any training data for any of these types of regions of the phase space or the phase diagram. So conclusions is that we introduced Born machines, and we provided an overview from the 2021 reference of the procedures for training the machine, evaluating the training loss per iteration of training in different regions of the XY phase diagram, and to identify prospects of this framework for other models with different underlying probability measures. We introduced the 6-vertex model, quantum 6-vertex model, and the dilute Potts models, which can be used to generate training set data for other phase diagrams that can be identified with the Born machine. And there are many other types of models of interest, including quantum Ashkin-Teller or other types of quantum systems that could further be analyzed with this Born machine framework. And thanks for listening.